Then the second part of this class today is about the low-temperature thermochronology in Fennoscandia. So, although said that this is a method that has not been very much used here, this is not exactly true. There's been quite some work done. But before we go to look at those data, we look very quickly about the thermochronometers in general. And then we look at the geological history in Fennoscandia after the end of the orogenic times, Svekofenian times. And then we look at some apatite fission tract data, and we look at some recent uplift and erosion events that have presumably taken place here in Fennoscandia. Looking at the thermochronometers. In the morning, Dave already described the concept of the closure temperature, so the temperature at which the diffusion of the different radioactive products in the hosting crystals is actually stopping. Now, depending on the system, which is here a selection of the most common thermochronometers from potassium argon to uranium, thorium, helium, and fission tracks using different minerals, we can get actually a quite wide range of closure temperatures that we can man with these methods. And the ideal case would be like here, that like this sample from the Swiss Alps, several methods have been applied to the same sample. So we have rubidium-strontium ages, which correspond to relatively high temperatures. We have potassium argon for muscovite, potassium argon for biotite, and fission tract data from zircon and apatite. And as the table shows, you can see that they correspond to different, like the fission tracks from zircon correspond to something like 240 degrees, and apatite something like 110. And depending on from which minerals we do potassium argon, hornblende, or micas, and which micas, you get a different thermochronological temperature estimation and time. So you can see that what this would then mean is that this is actually the kind of a cooling of an orogenic formation from the thickening and the orogenic peak. You can see very rapid decrease of temperature in about 20 million years to about 18 million years ago, and then it starts to cool down. And we are currently seeing apatite fission tracks, which shows that the leads from the outcrop were exposed to temperatures less than about 110 degrees about 7 million years ago. So having this kind of a data set from different minerals provides actually a complete data set for understanding the exhumation process. But for the shield areas, like here in Finland, these methods are commonly not used because most of the geological interest in Precambrian areas is related to the original formation of the rocks, the crystallization of the granites, of the gneisses, of the intrusions of the dikes. And then we're using typically thermochronometers which are high temperature methods, like uranium-lead method in zircons, which corresponds to temperatures of about 800 degrees and more. They're very practical for studying the partial melting processes in the high temperatures, and single crystals, as you know, can reveal a multi-phase geological history because of the zoning of the different layers in one single crystal. But this is a high temperature field. We are interested in the low part, and the low temperatures at sea starts from here, from rubidium-strontium. Rubidium-strontium, by the way, was one of the first geologically applied methods of age determination. because rubidium and strontium have high concentrations in normal rocks, and they are present with typical minerals like carbonates and etc. So it was easy to analyze those and run these analyses already in the 1950s. Well, then, Fennoscandia. The Fennoscandian geology is a result of several billions of years of evolution. The oldest rocks in Fennoscandia are about 3.750, at least the oldest zircons known in Finnish Archean. But most of the Archean was formed about 2.7 giga-years ago. Then we have the Proterozoic time, which resulted in this Fecophenian orogeny and mafic intrusions. When the orogeny was over, there was an important period of so-called anorogenic Rapakivic magmatism. And when all these major events were over, we speak of the later Mesoproterozoic, Neoproterozoic, and the Phanerozoic evolution. Now, we had mountain ranges here. The mountains eroded down, probably already by this time. And then there's been later evolution. What we know geologically, we have here and there on the time axis, we have dikes that are cut on the crust, and there are also alkaline intrusions, there are also kimberlites. And here and there are sedimentary rocks. This figure and many others I've taken from Rämön and Kohonen from their compilation in this book on Fennoscandian geology. On the geological map, here, the white area and the yellowish one tone correspond to the Proterozoic, lower Proterozoic and the Archean rocks. So most of the area in Finland and here, so it means the central part of the Fennoscandian shield consists of these old rocks. But we have these marine basins, the Baltic Sea, the Bothnian Basin, also the Gulf of Finland, and we have also the deep lakes like Lake Ladoga. Finland is a country of 100,000 lakes, but all the water in the Finnish lakes can be poured to the basin of Ladoga and doesn't even get filled. Because this is very deep, it's up to 400 meters deep in the northern end, whereas most of the lakes in Finland are just a few meters. Anyway, it means that this kind of a deep structure is actually a rift, and this kind of a rifting has been there. So what happened after the Precambrian orogenies and the denudation of the orogenic topography was that there were also extensional structures. Here in Satakunta and Muhos, there are Precambrian sedimentary rocks, unmetamorphic sedimentary rocks. These are sandstones, and these are clay and siltstones mostly. And these Precambrian sandstones are also quite widespread in the Bothnian Bay. You can think the Bothnian Bay as a kind of because it has not only these Precambrian sediments, it has also younger sediments up to about the Mesozoic. And so it is a sedimentary basin. So, reflection seismic data suggests that the thickness of the sedimentary rocks is maybe about 5 kilometers, something like that. And as Finnish side and Swedish side are lower Proterozoic mostly, it means that this is actually a kind of an extended basin, but maybe it tried to open to become an Atlantic, but it failed. It's just an intracontinental rift. And the big scale rifting took place in Norway, and there the Atlantic finally opened. But these are much, of course, these sediments are older than Atlantic basin and the ocean today. But Atlantic has opened couple of times. Okay, this is the situation. We have Rapakivi granites and younger than those and older than those, also younger and older sedimentary formations. Now, having this kind of a distribution of younger rocks, you can look at some of how the sedimentary rocks and the mafic dike swarms are distributed in the area, and you can see that we have a small occurrences of different kinds of dikes here and there. Mafic dikes of different ages, from Mesoproterozoic to Cambrian, Mesoproterozoic mafic dikes, and there has been also sedimentary covers. This does not show all the colors properly, I'm sorry. And then we have these sedimentary occurrences here and there. Now, then the question about what was the geological history like here in Kumpula is during the Phanerozoic. It's a question like asking that, was there snow last winter? Because all the snow has disappeared. It's difficult to say if there was any snow or not. There must have been sediments here, maybe, but how much, how thick, how long? That's one of the problems thermochronology may perhaps ask. Here's a detailed picture of Western Finland showing the Rapakivi granite, the Laipila batholith, and then there are the sandstones, which extend from the continent to the marine area, and it's quite commonly cut by horizontal sills of diameters. Very nicely recorded in reflective seismics, and also seen in outflows in Finland and Sweden. So we have had these extensional events, which has resulted in deposition of sandy sediments, and these were deposited from the continent all the way here. So this extensional basin of the Bothnian Bay and the sea must have been there already in the Precambrian in some form, because a lot of its bottom is covered with the Precambrian age sandstones. We have different dikes here, and as well as the sedimentary rocks. Now, often dikes have been interpreted as an indication of an extensional setting, because the idea is that in an extension there's less compressive stress. It makes it more easy for the melts to intrude. Maybe so, maybe not so. Dikes also intrude in compressional settings, and it indicates. But anyway, they indicate magmatic activity from the mantle at the time of their origin. And big mafic systems, dike systems, are known here in the Lake Ladoga, and they are about 1.4 gigayears, and the 1.25, 1.26 age dikes here in Western Finland in the Bothnian Sea, as well as also there in the sea. And these red numbers are neodymium epsilon values, indicating the origin of the rocks and their evolution in contrast to the mantle. So we have outcropping onshore areas and sedimentary cover, sediment covered marine areas around the central part of the sheet. Now, we can ask this question if we take a boat trip from Helsinki to Estonia to Tallinn. It takes a couple of hours only, and you're there. And if you go looking at the shores there, you can see nice cliffs and structures, and they are completely different rocks than what we have here. They are sediments ranging in age from younger Ordovician all the way to Cambrian. And if we look all the way from north to south in Estonia, you can see that there's a full sequence of sediments down to the Precambrian basement. So we have would expect to see this kind of material, and the cover is thin, so this horizontal dimension here is actually not, well, it could be that this is 100 meters, but really it's, okay, in the north it would be like this. When you go to South Estonia, the basement is at about 600 meters. So in about 150 kilometer range, the basement is tipping only about a degree or less, something like that. It means that if you extrapolate this back to the Finnish side, the sediments probably have been here as well. But what can we say about those? Were they ever sediments here or not? What do we know? Now, in terms of thermochronology, if we now have a crystalline basement and you add some sediments on top of that. So you would have here a layer of sediments, you have an original gradient, what happens? Tony. I add some sediments, I keep the heat flow the same. What kind of a thermal evolution you expect to see here in the basement? So if you have, for instance, 2 kilometers sediments.
It goes like if you
move my finger.
Let me think. It goes like steeper in left side.
So it would go like this.
Let me think about how it goes from.
This is the say before any sediments. This is your surface temperature 0, which is at the sea level, like here. It would be say 5 degrees. Then you add some sediments. What is the temperature then here?
It's T0.
Yes, exactly. And then you have a
basically same.
Yeah.
Same kind of.
And if you would start like this would be your initial case.
So it would be
finally
opposite that I said
yeah.
a moment ago.
It would go perhaps finer than something like this.
Yeah.
So you would expect to see in an outcrop here an increase in the panel temperature of a sample during the time of sedimentation.
What was the question?
So this is just the question, but this is the answer also. So that you have the initial one, you have the sediments, and then finally you would have an increased temperature. So if you have a sample here in the outcrop, in the presence of sediments that have disappeared now, there has been a warming of the sample like this. If then later the sediments have disappeared, you would have, of course, the temperature would have come back. Now this is the kind of a basic issue that we might be able to map with thermochronological methods, depending on which thermochronometer we are using and if they are sensitive to the kind of a problem we have. How much, by the way, if we assume that the heat flow here, heat flow is, let's say, it is 50 milliwatts meter square, and the thermal conductivity is, say, in the sediments would have been, say, 2. watts per meter per Kelvin. How much heating would there be after equilibration of the system? What is the maximum amount of heating from 2 kilometers of sediments? You can approach the problem simply like this. The heat flow is finally the same as now. Here is the first heat conduction law of Fourier. You can calculate from the heat flow value and the thermal conductivity what is the temperature gradient. What is the temperature gradient now? You divide the heat flow with the conductivity, you get 25 degrees. 25 degrees per kilometer would be the case. It means that from there your dTdz is 25 kilometers, and for 2 kilometers of sediments you would expect to see a heating of 50 degrees. So this way you can estimate what you would need to see in a thermochronometric analysis of a sample. If that would double that, then you would have 100 degrees. We return to this when I show you some results of apparatus pressure tracks in Finland. Now, so this way we can, and also in the Estonian case, we would estimate how much this has been heating of the Estonian basement with this layer of sediments. Okay. The problem of last year's winter and the younger geological evolution in central Fennoscandia are somewhat similar problems, and there are models and estimations what may have been there. It's an idea that in the mid-Proterozoic, after the Rappakivi intrusions have intruded about 300 billion years before, there was a time of sedimentary cover, and we have these sandstone formations and the siltstone formations in the bottom of the Baltic Sea about 13 million years before present, and it's speculated that maybe they have covered all the area, but here in the more uplifted out-exposed parts, these sediments have disappeared. Now, later there was a Sveko-Norwegian orogeny in southern Norway, and collisional events. This is also related to the Grenville orogeny in Canada, time-wise. And as a result of that, you had an orogenic front, you probably had a topographic uplift here. Could have also created some foreland sedimentation here on top of these sediments. And we would have obtained more sediments on top of those Precambrian sandstones. And then later, when we come to younger areas, about 700 million years, we would have this kind of a situation. There's a rift here with a question mark related to Ladoga, and also the extension of the Bothnian Bay and the Bothnian Sea. So that as we have some splinters of sedimentary rocks on the continent, on the Swedish side, it's possible that the sedimentary cover was there as well. Now, when we come to the Cambrian time, we have one interesting observation in the Cambrian. In southwestern Finland, there are nice glacially poised outcrops in the archipelago, and there are dikes. But the dikes are not filled with magma, they are filled with Cambrian sandstone. And this is an indication that the erosion surface must have been close to the present one, because sandstones do not sediment elsewhere than on the surface. So it's probably that this kind of an outcrop fractures were able to receive the sediments at that time, and that's often used as a kind of a tying value on the time axis about the elevation of the surface. And then here was also the Japetus Ocean, because the Atlantic opened for the first time, and maybe affected this area as well. And there could have been some sedimentation related to that. And then we come to the Caledonian orogenic front, when the orogeny takes place, and there was a subduction to the west when that time Atlantic basin closed. And the foreland of the mountain range, of course, experienced sedimentation. Just like today, in the Alps you have, excuse me, I'm making mistakes in the Alpine geology, but there were molasses, and there were also the sediments which extend far away from the mountains itself to the north. And so that was the case. We can estimate as the sedimentary cover can be correlated with the orogenic materials. And then we are jumping now all the way to 30 billion years, from which we know that there was a major river system in Fennoscandia which transported material along the Gulf of Finland and the Bothnian Bay and the Bothnian Sea via Baltic Sea to the North Sea. Actually, the huge accumulation of sediments that are carrying the hydrocarbons today, their provenance is actually Fennoscandia. Estonian geologists who have been studying this, because they have the sediments and they can study many features there, they have already named this system as the river system Eridanos. Eridanos comes from the Greek mythology. It is the river where the barbarians were sailing somewhere in the north. It's a nice name, Eridanos, but it's a good name. So the Eridanos river system was bringing a lot of sediments to the North Sea. In the end of the class, we return to this topic. So there's a lot of sparse information here and there on time axis, and also spatially in different locations of sedimentary covers and dikes in the area. So, and the present geology, once again, looks something like this. So we have the Precambrian exposed shield, the Caledonian front, and then we have the failed rift of the Bothnian Bay with the sedimentary sequences there. Unfortunately, they are under the sea, and they are not very easy to study. Plus, we have some alkaline intrusions and etc. So, and these magmatic activities about 360 million years. It correlates with the Caledonian front, but it also correlates with the Ural mountains of the east. Now, there has been then a number of studies on working with the apatite fission tracks. One of them, one of the very first ones, was made at this university in the 1970s already. It was Jyrki, yes, thank you, who made a first apatite fission track study in Finland. And you know, apatite fission tracks, the method is such that you're looking the apatite crystals and looking for radiation damages. So when the uranium-235 decays by fission, it breaks in two parts, and these are shot with great velocity to the medium, which is the apatite crystal, and it behaves damage. And this damage is the fission tract. And the more fission tracts you have there, the more time the crystal has spent at temperatures below the closure temperature. Because above the closure temperature, the tracts are healed. They are self-healed. The recrystallization of the apatite takes care of destroying the tracts, and this way you can do it. So this gentleman did this work, and at that time he had to do it manually. So he was calculating tens of thousands of tracts by eye under the microscope, and he got results. They were showing much younger ages than were expected for uranium lead, of course. And somehow the result was kind of ignored. And it was not really taken into account, and it was not continued. And he was also quite frustrated because of this silly calculation on the manually and using manual grids on microscope images, etc. But it was the basement of the work that was done, and his 80s were around 800 million years, which is not bad in comparison to these results by Glenn Murrell in his thesis in 2001, and with his supervisor Paul Andreasen, they published a paper in 2004, and they discussed a number of samples in different parts of Finland, and these are the apatite fission tract full ages of the different samples. It's black and white, not easy to see the kind of a pattern there, but one of the important things is that now when you have different thermochronometers, the temperature history of the sample cannot be solved uniquely. There's an infinite number of different thermal histories that theoretically can provide you the results you could see in the sample. Therefore, you have to map the probabilities of different solutions. And this is done like in this case, you can do Monte Carlo simulation, so that this is an enlarged part of some of their results. You have here the time axis, 1200 million years, 200 million years, present time. Here you have the final temperature on the surface, 0 and 150 degrees. PAZ is the partial annealing zone of apatite fission tracts. And then you have here the model temperature history. Now this is done so that you're doing a lottery with models. You're defining a discretization in time, and then you give some a priori, so pre-assumed temperature ranges that are acceptable, and then you do lottery. You calculate all possible different variations. You calculate what is their effect on the thermochronometer applied, and then if that's okay, the model is accepted. And then you redo this, and you redo this thousands of times. You will redo this kind of an exercise on Friday when you exercise with PQ, because this is just the PQ based results. Now, with this kind of approach, you can then calculate the possible thermal history of a sample, and in this case, as they are using fission tracts, only in this paper by Murrell and Andreasen, you can see that what the results seem to indicate is like here. There was a high temperature before about 800 million years ago. Then there's a relatively rapid decrease in the temperature. It would mean erosion and exhumation, and then there would be a reaching of a surface temperature about 550 billion years ago. This is actually the Cambrian peneplain assumption. They have nailed down this value here. And after the Cambrian, there was a mild warming, cooling, and a final. In the last 100 million years, this model suggests that there was a warming almost to the partial annealing zone. Now, in fission tracks, the modeling is based on the fact that the track length reflects the time, how long the sample and the track has experienced a kind of a healing temperatures. And the track length distributions are then actually modeled with these. So there's a forward solver of the problem of calculating how long tracks you get when the temperature is this and this high. And what D-Cube is doing, it calculates the distribution of track lengths as a function of the assumed thermal histories, and tries to fit that with the data. Oh, okay, this is the complete data set, and you can see, you can't really see the time axis in this picture, but you can see that what is common here is the Cambrian peneplain assumption, which is always peaking here about the same time. So that is not a result, that is an assumption. And then you have these variations. So it seems that if this is true, and all these heatings, the later than Cambrian heating and the recent in the last 100 million years, they seem to be repeating practically in all samples. So it means that thermochronologically in the last 600 million years, we have had events here. It means, and what does it mean if you have high temperatures in the paleotemperatures in terms of geological history? Of course, it means sedimentation. Now, already when Glenn Murrow presented his thesis, he actually was using not only appetite fission tracks. He had a kind of a hybrid model that includes also the argon-argon and the potassium-argon systems, as well as also the low-temperature uranium, thorium, helium there. So, and he attempted to and managed to give a sort of a thermal history all the way down from the cooling from orogenic times to the more recent thermal history. This is for the Archean crust in eastern and northern parts of country, and this is the Proterozoic in the west and south. So what we again see here, this is nicely the cooling from the orogenic temperatures, relatively late although, but it means that maybe there has been a continued slow exhumation taking place, because the peak of the orogeny was about 1.8 gigayears. Now we still see a quite significant kind of a cooling at about 1.6 gigayears ago. So the orogeny was around here. So well, it fits in the picture. These kind of tools are now available in thermochronology, and there are two major codes available. D-Cube is one of them. But what these give you is that they give a possible solution for the fission track distribution lengths. It does not control the geological evolution. That's something we have to do when we use the code. We have to have a reasonable model, and like these assumptions, we can nail down the constraints for any time here in the model, and require that the model fulfills that. This is something that needs information outside this model, but they're very, very interesting and practical tools. This is Glenn Murrow's picture as symbols how ages are distributed in Finland in his data set. But this is much more illustrative. This is a presentation from a compilation review paper by Hendricks et al. They compiled a database of appetite fission track age data in Fennoscandia, including the Norwegian mountains especially. They have very young ages. You can see the red color. Most red color corresponds to 70 million years, whereas the most blue is over 800 million years in Eastern Finland. We have in fission tracks we see this kind of a trend. So in a simple interpretation, it says that the Norwegian mountains were exposed to temperatures less than 110 degrees about less than 100 million years before present, whereas in most of Finland it took place already several hundred million years ago. So like we have high mountains eroding down, but also there has been several orogenic phases here in the west and southwest that provided sedimentary covers also in the fall. And we would be documenting this fall, I think. Glenn's data were taken from outcrops. He rented a car, and with his girlfriend they drove all over the Finland and took the samples from roadside outcrops. Beautiful and easy and cheap. But they are outcrop samples. Now, in terms of the paleo temperatures, if you have a situation like this, that you have temperatures increasing downwards as normally, and here is your outcrop sample. So outcrop corresponds to that one. But when you go deeper, the deeper you go, the closer you get to the partial annealing zone, and the data should start to reflect that as well. And I think I did not. I forgot to copy that picture, but the kind of an idea is that if you have here you have like a fission track age, and here you would have depth. Here you have depth. So if you also have a kind of a temperature scaling here, if it is linear, you can say that this is say 60 degrees, this would be 120, this would be 180 degrees. Now, you already know how thermochronometers work. If the temperature here is 0 on the surface, and the let's say the rocks cooled like 800 million years ago. If you have an age of 800 million years, like from eastern Finland, how would this age distribution go with depth? Now, think that you have a borehole where the temperatures increase and you will have more samples all the way down. How should it go? So, this is the PAZ, partial annealing zone. Would it go like this? Would it be constant? Would it increase? So one of the challenges in thermochronometry in this kind of areas is as we have drill holes, the geotherm also affects the age, and then they must be a uniform picture of everything. So, of course, what kind of an age would you get if the rock temperature is by fission tracks, if in apatite, if the temperature is 180 degrees? Would you get an age? No. Would it be 0? Yes. About it would be 0. So at here you would have a data point perhaps here. Now, when you go down from here, maybe you would see something like this. That when you are crossing the partial annealing zone, the AGs decrease from some values close to 800 or something, and they go down close to 0. So this partial annealing zone, temperatures between 60 to 120 degrees would mean 0 in practically the age. So you would expect to see this kind of a variation in the case the temperature profile hits the partial annealing zone, which would be very interesting because then for erosional models you would have your data would also tell, you would know where the partial annealing zone is today and how that relates to the ages.
In this study,
Please.
we can have a solution of this type for each ages in aperture fission flux, because if you stay more or less in the past, you can have a length distribution like you want.
But the observations constrain that quite efficiently. So it's not completely free, but you understand that the track length distribution is. So the basic thing is that if the cooling takes place rapidly, you will get a very sharp distribution, and the tracks have almost an ideal length. But if it happens that the cooling is slow and some healing takes place, you will first have this kind of high values, but they get shorter, and you start getting distributions in this direction. And the distribution is, of course, it's theoretically it's a normal distribution originally, but it becomes more skewed because of the cooling events. And if there is a reheating, it could be even there could be even two peaks, two modes of the distribution. So I think on these days you will hear very nice analysis and explanation of this in more detail. So it is not completely free, but you can see from the models. Okay, so the buffer is so like here. So you can see that the thin line here, thin solid line, gives the boundaries of the accepted models, and the black one is the average of them all accepted. But statistically, we can place almost anything between these boundaries here. So this is the field for geological interpretation then. What remains after this model. But this is a good thing that you can run these models also without any constraints. You can see, and I will show now a couple of examples of a work we've done with Paul Andriesen, taking samples from a deep borehole in eastern Finland. There's a 2.5 kilometer deep borehole, and the bottom temperature of the borehole is 40 degrees. So it's not yet in the partial annealing zone formally. And I have here two examples. This is a sample taken from 157 meters, and the inversion with big Q gives a result looking like this. So we have this box gives the initial assumed boundaries more or less. Here the final temperature is constrained by the borehole temperature, because it must meet the borehole temperature approximately. And the result is that what you can see here. Dave, what could you say? Not much. Yeah, you can see anything you want, but actually what it tells that your thermochronometer is not on. It's not zero, because the temperature today at 157 is less than 10 degrees. So it's very low temperature at the moment. So and therefore this does not give really an indication of reliability of anything. But here when we go to 1.8 kilometers, and we are approaching the temperature of, let's say, maybe 35, 36 degrees, you can see that the results suggest that the sample has spent some time in the partial annealing zone and cooled below the partial annealing zone about 150 million years, 100 million years at least, and about 50 million years. So relatively recent. So now our sample is deep enough, and it seems to tell some sort of a story with this thermochronology. Now, in appetite fission track ages, those kind of overall ages or pooled ages are kind of an averages of everything. And you should very carefully interpret those. They're just kind of let's say, mathematical tools to widen number of the results. And we should be quite careful in interpreting this 800 million years of a given age for the sample. So it's not really indicating of even of something. But those data in the countrywide, they suggest that there is a difference between the thermal evolution of eastern part and the western part, and between Norway and Sweden and Finland. Then the final part of this class today is about the Eridanos river system. Now, there's a lot of research carried out here in the North Sea because of the hydrocarbon deposits. There's a huge amount of research and drillings done, and one of the important observations from our problematics today is that the provenance of a lot of the sediments in the North Sea, especially in the Cenozoic and the later times, are derived from Fennoscandia. So the provenance is Fennoscandia, and there are useful gravity topographic laws like here across southern Sweden, where you have the big lakes and there's also quite low valleys. We have the Baltic Sea here, and we have the Baltic Sea and the Gulf of Finland. And the model is, and the observations support the idea that there was a very strong deposition in the North Sea basin in the last 10 million years, and the sediments were derived from Fennoscandia. Looking at the present topography and bathymetry in Fennoscandia is nice, because this tells you now, you can see the basins and the continental shelf here in the north, and the oceanic deep basins here in the west. You can see the mountains, and you can see nicely how the topography and the faults are cutting that. And there's a lot of transport directions from the mountains to the Baltic Sea. Here, the topography in Finland, the texture is mostly due to the glacial landforms produced by glacial quaternary deposits. But in the north, part of the higher topography is related to the uplift in the last, say, 50 million years in the north. But start looking at the intercontinental basins, the Baltic Sea, the Baltic proper. You can see that there are quite deep and areally limited constrained basins. Here, when you come to the Åland area, you have a very deep basin here, and you can follow these structures all the way to the north. They are not completely continuous, but the kind of an idea here is that the Eridanos river system was actually working through these basins, and some of these structures are interesting because we are not able to say if they're due to a glacial erosion or if they are due to a river erosion. When you look at the details of the bathymetry here, this is a very nice looking spot, because if this is above the sea level, and you would have water flowing, you would have here a narrow gorge of a river, and here you would have waterfalls. I would call them the Åland cataracts, and you have a deep kind of a basin here. As I'm not a geomorphologist, I'm not able to right away give an interpretation of this, but one of the basic facts of erosion is erosion takes place when the surface is above the sea level. And very deep channeled erosion takes place when you have a lot of topographic potential. So in a peneplanized topography, the rivers are meandering and they are slow. But if you have a high topography, it's possible you might have much shallower structures. If this is glacial erosion, then it's possible it's done under the sea level maybe. It could be a part of the story. But anyway, when we compare what we know about the geology here in the barren areas, you can see that the deepest parts of the basin are also the oldest. The number 8 corresponds to Mesoproterozoic sandstones, and they are also present all the way here up to there. And the deeper the basin, the older are the rocks outcropping there. It means that if you have a horizontal layering of rocks, so the deeply incised river channels would hit the oldest rocks in the deepest parts. So, and we have these topographic, bathymetric features which may be related to this erosion and transport in this Eridanus system. This is geological timetable. This is the depth data and bathymetric data of the basins in the Baltic Sea and the subseas. So we have these values, and the deepest basins are actually quite small and isolated. So this is really an intercontinental basin. And coming back to this Eridanus system, so the idea is indeed that the North Sea sedimentation in the last 10 million years is largely coming from Fennoscandia. There are geological information derived from the drilling data in drilling cross sections. This is data by Uberem and co-workers showing the sediment accumulation rate. The scale here is in millions of years. You can see that the sediment accumulation rate increases after about 5 million years before present, 4 or 5 million years before present. And also the uplift rates in Fennoscandia, especially the west, they are studying the Norwegian areas. And the paleo water depths are actually decreasing, which corresponds to the uplift. And the same with the subsidence decreases. Now, this, in a way, it would indicate that indeed there's an enormous deposition taking place in the last in the last 10 million years and less. And we can make a simple calculations. If the river system area is like this, it may have removed something like 250 meters of rock rapidly. In 10 million years, it would then be same order of magnitude as the sedimentation in the North Sea. If this is the case, I don't want to swear on it, but it's really possible that we have this kind of a system. Then the good geodynamic and the geophysical, geological question is that if we had this erosion, we must have had uplift. Is this then the time when the shield became the shield? Was this the time when part of the central Fennoscandia was uplifted, the sediments were removed, and the sediments were transported, for instance, to the North Sea? Therefore, as a kind of a conclusion, that there are a lot of undiscovered issues in the low-temperature thermochronology in Fennoscandia. And I may add a point of information from a completely different field of geoscience studies. In the dissertation work by Riikka Kiertäväinen, which was accepted in the spring, she presented results about deep fluid studies in this Outokumpu deep borehole. And one of the observations was that she was able to show with noble gas isotope analysis that the residence time of helium in those fluids in deep fractures was of the order of 10 to 50 million years. Now, if this is the case, it would mean that it would run hand in hand with this idea of relatively recent uplift of the shield and the recharge of the fluids about, say, 10, 50 million years. Maybe I'm jumping too far to conclusions, but this is nice in science that we may have ideas where we combine things, and this question about when did the shield become a shield is still actually not properly answered. So, thank you very much for your attention. If you have any questions, so I would be glad to answer. I will be around all the week, all the time I can, and I would be happy to discuss with you also these issues later if you like. But I'm very much looking forward to these 3 days of foreign specialists giving presentations in each of the topics, so you'll be bathed in top information on